All right, hello everyone. Welcome to Achieving Trustworthy Biomedical Data. I'll go ahead and start us off with a intro presentation. Dennis, do you want to actually start us off before we?
Yeah, sure. Hey everybody, this is an exciting opportunity to dive into what I think is one of the hottest topics of our time really for precision health. And that is the ability to strike a balance between the advent and increasing availability of digital tools for better healthcare and medicine, better health management, and privacy. How do we strike that balance, and where do we make good trade-offs that are acceptable to embrace these digital tools while also maintaining what I think will be a dynamic landscape of privacy over time? Peter's assembled a fantastic slide deck and we'll take charge in a second here. And today's session will be focusing on some exciting submissions that I hope you will find tantalizing, as well as hopefully a look to the future for maybe another session in the new year 2022, actually, where we might be all together again on the Big Island and have an opportunity to really dive in deep on this discussion. So thanks for attending. I know this is not the most optimal vehicle through which we can communicate, but let's do our best. And Peter, take it away.
All right, thank you, Dr. Wall. So welcome everyone to Achieving Trustworthy Biomedical Data. I want to give a huge shout out to the session organizers, Professors Wall, Tatanetti, Liphart, Percha, and Young. It's been an honor, and I've been lucky to get to work with such a rock star team. Before we get started, I want to give a note that everyone should tweet your discussion questions and questions for the session papers with the hashtag DataTrustPSB. Here's a little picture with an example. I'll be monitoring those. If you don't have Twitter, it's okay. We will also go through questions in the Q&A, but we will prioritize the Twitter ones. So data privacy is increasingly at the forefront of public discourse. We see this in many ways. We see it in commercial genomics with 23andMe and Ancestry, which have all of our SNPs, and unfortunately they're vulnerable to attacks. And they also learn things about us with our DNA that we might not have consented to originally. There's also commercial products like Amazon Alexa, smartphones that are increasingly doing things in the name of health. And really, they're getting all of our data in the name of health. So we should think about, is that okay? Is everyone okay with that? Do we know everything that they're really doing with our data? There's also face recognition and surveillance, which most recently has been used in the name of health for COVID-19 surveillance, which you could argue is a good use case, but then there's some maybe not so good use cases. For example, China has been using AI and face recognition to profile minority groups, and you could imagine other use cases that might not be optimal. There's also the issue where you might post a photo on social media and you think you're just sharing that photo, but as AI gets better, people can use that AI to predict things about you from the photo, and maybe the things they're predicting about you are not things that you had originally consented to being public. That's this and many other reasons are why everyone is starting to talk about data privacy and why biomedical data science as a field needs to think about these issues more in order to garner the trust from the public to use these solutions that we're all creating. And of course, a lot of the community in BMI has come up with some great solutions for achieving trustworthy data and methods. So we'll do a brief overview of just some of those. One of them, which is not technical, is the law. So that's HIPAA. I'm sure most people here are familiar with HIPAA. It stands for the Health Insurance Portability and Accountability Act, and it requires healthcare providers and others to be compliant with a set of regulations. There are other regulations, for example, by the EU and other sources, but as I'm sure we all know, there's always this delay between tech innovation and science innovation or discovery, and the law catching up to that. And you could maybe think about deepfake as an example where there are not laws, but maybe bad use cases of that. So in terms of tech solutions, one way we can address it is data transformation, where if you can have a machine learning model that can have just as accurate prediction with data that's been privacy preserved, then you might as well privacy preserve that data. And here we have an example by one of the session co-organizers, Professor Young, where she was using depth sensors to transform these images, and now they're privacy preserved, of hand washing in hospitals. And that altered data set performs basically just as well in predicting hand washing compliance. There's also been data transformations in genomics. And it's also important to transform these data because hackers these days are using machine learning for more complicated attacks. And we're going to have a super exciting session paper that will be presented on shortly about one such attack called a membership inference attack. I'll let that paper, I'll let them talk more about this, but they introduce a really cool technique, which they profile, called differential privacy, which in one sentence is injecting smart noise into the data, and then any querier of the data is receiving data that's where each row in the return data is not real, but in aggregate, all the properties are preserved. So cool technique, and we'll hear more about that shortly. There's also federated learning, and you could think of federated learning as distributed machine learning. So imagine you have a bunch of hospitals or healthcare providers that are each trying to train the same type of model, but they don't want to share their data. So what you can do is you can train a local model for all of these independent data sources, and then instead of sharing any of the data from the hospitals, just share the learned model weights locally with a central server that will only, again, see those coefficients of the model and not actually see any of the original data. It could aggregate those, get a really good global model, and then you could actually redeploy that global model back to the local settings, refine them through transfer learning, fine-tuning, other personalization techniques, get an even better model, further train it, re-upload the weights, and you get this closed loop system where you're continuously improving the model with everyone's data, but in a privacy preserved way. Also, if we want to get people to trust data, we need to have explainable AI. So there's models like linear regression, which is inherently explainable, y equals mx plus b. Pretty easy to understand how the predictions were made there. But other techniques like deep convolutional neural networks, not so explainable, especially when they're very deep. There are some methods still to try to understand why they're making the predictions they do. One of them is a black box approach called a saliency map, which in short is changing each of the input pixels going into the CNN and then measuring how the output probability vector changes. If it doesn't change a lot, then that pixel is not too important. If it changes a bunch, that pixel is very important. You do that for all the pixels, and then you can get a nice visualization of which parts of the images and the input were useful for the model in making its prediction. For health records, there are a ton of different approaches that have been proposed. One of them is encryption and different ways you could apply encryption cleverly. Another one is to have a proxy to the data. So instead of any client directly querying the database, they can query the proxy, which will then, they will query the database, and they might not even return the original data. They might return a smart noise version of that data. If we want to have trust in data, we also need to have representative, fair, and unbiased data. And there are some techniques in tech to solve this or help solve this, one of which is balancing data through, for example, generative methods. Those will work a bit, they will help, but they're not the entire solution. I think that at the end of the day, in order to get truly representative data, we need to have balanced data collection and data curation, but we can talk about that in the discussion. A lot of machine learning is centered on crowdsourcing, crowd labeling, especially for massive data sets. However, it's hard to do that when you have PHI, which is protected data. Maybe you don't want any crowd workers to see that. So if we can filter crowd workers, give them credentials and trust them, then maybe we can get those data streams labeled as well. And whatever we do, whatever tech solution we come up with, there's always bioethical considerations to make. And oftentimes they actually contradict each other. So for example, let's say you're talking about surveillance and you think that, well, it is going to do good to everyone. That's a utilitarianism argument, to surveil everyone, because if you're doing that, then everyone will be monitored and safe. But it might be going against Kantian ethics, where it's going against a fundamental principle or universal law of don't invade people's privacy. So, different decisions you make can follow different theories that people have been talking about for many years. So, brief introduction of our session papers. We're going to have that differential privacy membership inference attack paper, which is going to be super exciting. We have a poster paper on COVID-19. Everyone should check that out. It's, in short, exploring how we can use real world data to supplement data from RCTs to both allow people to receive treatments earlier, but also to potentially speed up the RCT process. Then finally, we'll have a presentation on the selection of trustworthy crowd workers for PHI data. So thank you everybody so much for coming. Don't forget to tweet your questions to #DataTrustPSB for, again, both the session paper questions and the discussion questions. And without further ado, we will get to our first paper.
Thank you, Peter. And yes, again, please tweet out your questions. We'll have a Q&A session that begins at 11:15.
So our first paper is by Chen et al. From Temple University. So here we go.
Hello, everyone. I'm Jingjie Chen from Temple University. Thanks, PSB committee, for giving us this opportunity to present our work. In this work, we investigate whether the deeper privacy is an efficient protection against the membership inference attack, machine learning for genomic data. This work was collaborated with Professor Wang and Professor Xu. In this presentation, I will first briefly talk about the membership inference attack machine learning models and two defining strategies against MIA. These are our results on genomic data and the conclusion. As the growth of genomic data, the study of genomics is becoming a big data science. It's critical to collect a large sample of genomic data to build up a more powerful machine learning model. Since the genomic data is naturally sensitive and private, sharing such data has potentially risk to disclose one's private information. Some studies have shown that not only the raw data, but the trained model can leak one's privacy. An example is the membership inference attack, by which an adversary can infer whether a sample is in the trained set of the target model. Here's a scenario of a membership inference attack. A cancer treatment center collects a lot of patients' genomic data and trained a machine learning model on this data. Then they release their model to public access. For normal users, they just upload their genomic data and get the predicted result back. However, for attackers, they can do much more than the normal users. The attackers can upload anonymous data and get back the predicted results. Then they can infer whether this person has ever been a cancer patient in the cancer treatment center. So let's have a look at how they can do this. There's a sample trained by the service provider. We call it the target model. This model can be accessed by the attacker. The attacker input a sample into the model and get the result back. Then infer the membership of this sample just based on the the returned probabilities. In general speaking, it's a binary classification. The attacker first have to train a shared model which mimic the target model. To train the shared model, the attacker have to collect a large set and select the part of them to train the model. Then the attacker can train a text model based on the output of shared set. The samples in shared set is labeled in, and the samples in unused set is labeled out. Once the text model is done, it can be used to infer the membership of the samples. To mitigate the attack risk, we can add noise to the target model, which can result the prediction probabilities are not exactly accurate, then reduce the attack accuracy. In this work, we adopt DP to predict a target model by adding noise to the weight of a target model. In machine learning, the DP noise is usually added to the grading of each step. Thus, the noise can be accumulated. So we have to turn the hypermeters such as the training steps, a noise size to control the DP budget. A small DP budget can provide a strong protection, while the utility of target model can be largely hard. So it's important to find a balance, find a good trade-off between the privacy protection and the utility of model. Besides, some studies have shown that the vulnerability of a model is due to the model overfitting. Thus, the techniques that can inhibit model overfitting can be helpful against the MIA, such as the error norm. So in this work, we investigated the DP and error norm on two popular used model, Lasso and the CM-based deep learning-based method for ACE genomic data. This slide shows the impact of error norm and DP budget on Lasso model. The left panel shows the impact to target accuracy. The accuracy higher is better. And the right panel shows the impact to attack accuracy, lower is better. The top two dashed lines are Lasso model without DP. We can find the sparse Lasso can achieve higher target accuracy. At the same time, the sparse Lasso can reduce the attack accuracy, which demonstrates that error norm can inhibit the model overfitting and achieve higher performance on test dataset. The two solid curves represent the relationship between attack accuracy and the DP budget. When the DP budget is small, it can largely reduce the attack accuracy, but it can also badly hurt the utility of target model. We also noticed that the sparse model without large DP budget little drops the target accuracy while provide a strong protection. So combining the error norm and DP budget is a better choice against the MIA. We can find a similar conclusion on CM model. The sparse CM model without DP achieve a higher target accuracy. At the same time, the sparse CM model can reduce the attack accuracy. And the CM model with L1 and the DP provide strong private protection. We also noticed that the small DP budget lead the attack accuracy varies dramatically. It might be because the CM model has more weights and more complex than the small model. When the DP budget is small, it will introduce large noise to the weights and result the output of the model is unstable. In this work, we find the machine learning model has a risk to leak privacy against the MIA. DP alone can defend against the MIA on genomic data, but it will hurt the utility of a target model. Combining the model sparsity with DP together can mitigate the risk of MIA, while little hurt the utility of a target model. So, thank you for your attention. I'll take any questions.
All right, thank you so much, Junji. That was a really great talk. As a reminder to everyone, post your questions to Twitter with hashtag DataTrustPSB, or feel free to put them in the Q&A if you don't have Twitter. To start us off, I have a question. So in this case, the baseline models without the DP and without the regularization, the attack model still had a relatively low performance. So like the attacker can't be too sure. Are there biomedical data sets where the baseline attack model have been shown to be like pretty good? I think you're muted.
We can't hear you. Let's see. Junji, you're on. It looks like you're not muted, actually. Are you speaking now? Can you also maybe answer in the Q&A? Is that possible? Type the answer.
Sure, we can operate with that for now.
We have another question that's come through, but hopefully we can hear the answer. The question is, you used a yeast data set, but do you expect to see similar performance using a human genomics data set? Again, typing the answer might help. If you have that ability. Uh-oh, the mic does not work. Well, one other option would be for us to save these questions for the Q&A session at the end. And by then, perhaps you'll get a way to be heard, Junji, like calling in as just suggested. Why don't we work on that separately, Peter, and move ahead with your presentation.
Sounds good. So yeah, the next talk is my talk. So I guess here we go. Hello, everyone. My name is Peter Washington. I am a PhD student in the Wall Lab at the Stanford School of Medicine. And today I'm here to talk about the selection of trustworthy crowd workers for telemedical diagnosis of pediatric autism spectrum disorder. Autism is a condition that affects 1 in 40 children in the US, and it's characterized by a lot of phenotypic characteristics such as lack of eye contact, trouble with social responsiveness, and a host of other characteristics. Unfortunately, there are several diagnostic bottlenecks to receiving a diagnosis. A big one is that the waiting time for current standard of care on average exceeds 18 months in the US, which is incredibly problematic because for a child, the longer you wait to get a diagnosis and therefore start treatment, the less effective that treatment becomes. Another bottleneck is especially towards making these diagnoses go in the home and in a scalable, translatable way, is that the diagnostic questionnaires are extremely long, hundreds of questions. But prior work, including by the Wall Lab and most recently in last year's PSB proceedings, have shown that you can do feature selection and identify a small subset of the questions asked in those questionnaires to get a reliable, accurate diagnosis. Finally, these bottlenecks, especially with the waiting time, are systemically discriminating against marginalized populations, which is, of course, problematic. So what we need is a scalable method for rapid, fine-grained, and accessible diagnostics. And crucially, this process must be privacy preserving and trustworthy. And that's the aspect that we're gonna focus on today. The framework that we operate under is this idea of crowd-powered AI for diagnosis. And the way this works is that we have a bunch of humans watch videos of children who might have autism or might be neurotypical, and they answer a series of multiple choice questions about those videos. And in doing so, they're transforming this incredibly complex space of multi-dimensional 4D tensor of pixels into a one-dimensional categorical ordinal feature vector, which is much more amenable to machine learning when you have smaller amounts of data. And so what we do is we take those generated feature vectors and use those as input to a machine learning classifier, in this case, logistic regression, and that will be trained to output the probability of a child having autism. And fortunately, logistic regression is a calibrated model, which means that the outputted probability could be a good risk score as well. And so the aspect of this framework that we focus on is identifying which crowd workers or which humans should be allowed to even see these incoming videos. And there's several reasons why we need to do this. The first is that image annotation, video annotation of human behavior is much more complex than simple object categorization or segmentation, which are the tasks that you typically see in computer vision. So if we're going to get computer vision that can reliably and accurately classify human behavior, then we need pretty good labels, and we can't just take any crowd responses. Another angle of this is thinking about privacy in terms of the incoming videos. And that's another paper that our lab has published, but we're not going to talk about that today. But it's worth mentioning because of the session that we're in. So yeah, we want to filter down the crowd workers to a small subset of trusted crowd workers who are then made members of the Stanford research team and can see these incoming videos that are potentially private. And so today's work is about how we identify those crowd workers. And the way we do it is by having them rate a few set of public videos that are balanced by diagnosis, age, and gender, and having crowd workers answer the questions for a bunch of these videos. And we measure behavioral metrics on the crowd workers. So one of those is that we have each worker watch the videos, generate the feature vector, and then wait a month and then recruit them to do it one more time without accessing their previous answers. We measure the distance or difference between their answers, which is the L1 distance. And if the answers are drastically different on the same video, that's bad, and we don't really want to proceed with that work. For this study, we just record that. Another metric that we record is that we have each worker watch the video, generate the feature vector, and if they spend not enough time doing it, which we record the time, then we ask them to do it again, and we tell them, hey, we noticed that you spent an impossibly short amount of time rating that video, so with that in mind, can you revise your answers? We record their revision time and how their answers differ the second time. If their answers don't really change, then that means they probably just waited and therefore are not really trustworthy workers. But we record both their time and the amount that the answers change. And finally, we just look at the difference in their resulting feature vectors across all the videos that the worker rated, with the idea that if they're rating every video the same on a diverse set of videos, then they're probably just answering BBB on the test every time. So we quantify these metrics with formulae, and we need to then see how well they do. And we need an outcome measure, and the outcome measure we use is the mean probability of the correct class, which is actually a pretty simple metric. And the way it works is that if the true class of a particular video is autism, then the emitted probability from the classifier is the PCC for that video. If the true class for a video is neurotypical, then the probability of the correct class is just 1 minus the probability emitted by the classifier, because the classifier is always emitting the probability of autism. So we take the average of all those probabilities of the correct class for all the videos, and that mean PCC is our outcome measure that measures how good the crowd worker is. And we train a linear regression model that takes these metrics as input and outputs a predicted mean probability of the correct class for the worker. And so using fivefold cross-validation, we measure the mean average error of such a linear regression model. And we see that at its best, it can predict the mean probability of the correct class at a less than 7% mean average error. And that's using just this MPIL metric, which is this metric, how different they answer in all the videos. So that's great. That's really good, actually. That means we can use those behavioral metrics to determine how good a worker is going to be. But then we wanted to see, how is this going to generalize? So then we took all that data and trained a linear regression model. Then we recruited a separate set of workers to rate a separate set of videos, all distinct, so completely different set of videos, completely different set of workers. We wanted to see how well can that originally trained linear regression model predict on this new set of workers and videos. The mean average error went up a slight amount, which means there was a tiny bit of overfitting going on, but actually not too much. The mean average error with that distinct set of videos and workers is less than 11% at its best. And that's with two features, the previous metric that we looked at, as well as this metric, how much their answers change 1 month later. And we find that together, those two features are the most predictive of the worker performance. And so we've generated a method for evaluating the behavior of crowd workers themselves, which can be incredibly predictive of their performance later on. And so we can take these behavioral metrics and use them to recruit crowd workers who then we have join the research team at Stanford and go through HIPAA training, city training, official laptop encryption, and ultimately become get a Stanford account and become full-time research team members. And then they can get incoming streams of private videos that only official researchers can see. So thank you so much. I will take any questions. I especially want to thank Dr. Wall and the Wall Lab, as well as all of our funders and my thesis reading committee. Thanks.
Okay, we can take questions now. We have one in the Q&A, which I can read for you, Peter. Do the crowd workers display any bias towards preconceived stereotypes of neurotypical features? And are there any apparent cultural differences in the kids' personality and behavior that a crowd worker might not consider? So perhaps start with the first. Do the crowd workers display any bias towards preconceived stereotypes of neurotypical features?
Yeah, that's a good question. So the features that are being labeled are designed to be not specific to autism or not autism, but rather they're just observations that people make. So it's not the kind of the idea of this is that these crowd workers, while they're maybe good at labeling behaviors, they're not trained to have anything to do with labeling autism or any other developmental delays. So they're just rating things that you can observe. And then
related to that, perhaps to draw it out just a little bit further, do the crowd workers that you're recruiting know what they're doing specifically? Are they told in advance? Or if they were, could they not be perhaps? In other words, can we identify a crowd of workers who, and this is getting to the same question, who are good at measuring features without really knowing what it is they're measuring per se?
Right, yeah, none of them have any idea what they're doing it for. There's a monetary incentive for them, and they know that they will continue to get invited if they do well. But besides that, they don't really understand that this is
so perhaps that helps to mitigate or manage sort of priors essentially coming in with some preconceived notion about the way the world works or what it is they're measuring that would, in other words, sort of inadvertently bias the answers in one direction or another.
Right, yes, exactly. And then in terms of the cultural differences, there are other studies in the law lab that are exploring this, in particular in Bangladesh and Kenya. And the data is still coming in for that, but we will measure it and see what we find. I suspect there might be some differences, and we will adapt the methods accordingly.
Yeah, and I do think that, just to fill in on that, I do think they are adaptable. We have an interesting demonstration, published proof of concept of this sort of approach working in a Bangladesh population, but much more work will be needed before we really know how much adapting, how much moderation, and how many changes we need to make essentially to the process overall to be able to advance to different cultures and different cultural groups overall.
I think there's a few questions.
A new question. Yes, new question is, why a month? Can you determine a minimum amount of time that you need in between? I believe in between. Go ahead, Peter.
That is a great question. Yeah, so it wasn't chosen at random. I mean, kind of at random, but it was based on other studies on other types of reliability. I think repeat test reliability or something along those lines that showed that people just completely forget their answers 2 weeks ahead. So I chose a month because it was like, okay, well, the literature's saying 2 weeks. Let's just make it a month so that nobody can doubt it, essentially. But yeah, since the literature does show 2 weeks, it might be worth reducing it to 2 weeks to speed things up, and because it might still work. I think there are Twitter questions as well. I could
checking these out. Yeah, continue to tweet your questions. Hashtag DataTrustPSB. One question, Peter, for you is, can we use the worker's behavior as weights in the final prediction of a child's diagnosis?
Interesting. Yeah, that it could be done. It's worth exploring. We haven't explored that yet.
Yes, I think perhaps as the crowd grows and we begin, not only kind of grows in terms of numbers of individuals who are participating in the crowd task, but also the frequency with which individuals in the crowd are participating over time in subsequent tasks of the same type, we might be able to take advantage we would be able to develop a shape of their behavioral distribution and then leverage that for weighting. All right. It is now 11:15. We are exactly on time. I hope everybody's riveted, just stuck to the seat and excited about this particular subject. And we now are going into an open Q&A session that I believe will be handled entirely via the Q&A chat. We have, again, opportunities. Oh, wait, here we go. We've got another question here. Do you ever retest a rater to see if fatigue or experience changes their reliability?
Yeah, we have data on that. It's not fully in yet, but we have the same workers do the same task for many different types of videos, but they also do other tasks that are kind of related. So other behavioral features that are maybe not used for diagnosis, but used for training computer vision classifiers, but also for providing a diagnosis, like in a two birds, one stone way. So yeah, we're getting data in that as it's coming in, and we'll see what happens.
It's a great question.
There's one Twitter. There's can we use workers' behavior? Oh wait, sorry, you asked that.
Yeah, I'm trying to come through this. So we've got some good comments on our on the handle so far. So continue again to check that out. I want to come back to see if audio is now working for Jinji.
Yeah, I'm here.
Very, very good. Okay, so why don't we go back to the questions that were asked to you, which I can't see. Hold on. Peter, do you have them in front of you?
Yeah, I could start with mine, which was, so the baseline attack model was, still had relatively low performance, so although the differential privacy did decrease its ability to attack, it was already didn't have too good of an ability to attack. So I'm wondering if there are other biomedical use cases where the baseline attack model has been already pretty good.
Yeah, the accuracy of MIA is not very high because in our study we just use the binary classification. Some studies have shown that the accuracy of MIA may have a much higher accuracy on multiple classification.
Oh, Peter, we need to move to another Zoom.
Okay, let's start our discussion with asking Gigi the rest of the questions. So we will meet in the discussion Zoom. See you all there.